Okay, now it's time, and I'm going to start my today's session by the discussion of proof of Lagrange theorem, because I scanned through the question papers on the other day, and I found that Lagrange theorem proof actually used to come in the examination. Now, the proof of the Lagrange theorem in online examination, this sort of question is not going to definitely come, but the process by which the proof is done, that is actually very important. The proof is not that tough, and a few aspects about the left and right cosets may be clear from the proof itself. So I think if I do not do the Lagrange theorem proof in the classroom, that in that case the discussion of group theory will remain incomplete. So let's begin the discussion. Lagrange theorem proof. Okay, and the statement of the Lagrange theorem was like that: let capital H be a subgroup of a finite group capital G. Then the order of then the order of H divides the order of the group, Let us call the group to be capital G. Then the discussion will be easy to carry with. In particular, cardinality of G and the index set of G with respect to H, that will be multiplied by the cardinality of H. Now I'm going to as you can remember, this particular term is called the index. Now I'm going to discuss to begin with, we shall, as it is mentioned that the group must be a finite group capital G. So remember that Lagrange's theorem is only applicable to finite group. If the group is infinite, then Lagrange's theorem is actually meaningless, because then we have to deal with the cardinality of the infinite group, and which is always infinite. So to start with, we shall proceed in the following way. Since G is a finite group, and consequently the index of G with respect to H will also be finite. Okay, let us assume that this index of G with respect to H be a finite number, which is R. This will imply that there exist R distinct left or right cosets of capital G. Okay, so we shall without any loss of generality, we shall consider the left cosets only. The entire proof can be repeated with respect to right cosets also. This statement which I have written over here, that when index of G with respect to R is the index of G with respect to H is a finite number, then that number will define how many left cosets will be there for the group capital G. This statement is very important, and we will get to see that often we are going to use this particular knowledge to some other problems also. So therefore, this statement is also very important. If you have understood my earlier discussion on the left and right cosets by which the group is subdivided into different classes, then probably you have understood why am I saying that the index set of G, the index of G with respect to some subgroup of capital H, some subgroup capital H will define how many left or right cosets will be there. So let us assume a few R number of left cosets here. So let A1H, A2H, and ARH. These are the left cosets of H in G. Since distinct left cosets that we have defined above are mutually disjoint, what do you mean by the word mutually disjoint? This is not the same with mutually exclusive. Mutually exclusive is something else. If you have attended my class of second sem where I taught you probability theory, there I discussed about the difference between the word mutually disjoint and mutually exclusive. Mutually disjoint means you consider any two pairs from this left cosets, from this R number of left cosets, and you will find that these two left cosets will always be disjoint. Okay, there will not be any common element between them. So this word is called, this is known as mutually disjointness. So since these are distinct left cosets, they will also be mutually disjoint, and therefore the cardinality of the group will actually be the cardinality of the union of these left cosets. So I'm going to write it in this manner. Okay, so you consider the union of these left cosets, and their cardinality will actually be equal to the group's cardinality. But since they are mutually disjoint, so the cardinality of this union will be the sum of their individual cardinalities. So I can write it in the following manner. Okay, and we also know that from an earlier theorem which I stated in my last class, that cardinality of AH and cardinality of H and cardinality of HA, they are actually same. So all the AIH can be replaced by H. This is another theorem. I cannot remember whether I did any proof of this theorem, but if I have not done any proof for this particular theorem, then it is all right. You don't have to study thoroughly the proof of this result. You can only remember this particular result. Okay, this result which I am using over here. So how many left cosets are there? There are R number of left cosets, and therefore R number of cardinality of H's are there. So that can be written as R multiplied by cardinality of H. And as you have assumed that small r is the index of capital G with respect to H, so I can replace, in place of R, the index, this symbol G colon H, which will be multiplied by the cardinality of H. So see, we actually have correctly proved that the index of the group with respect to cardinality, with respect to subgroup H, is actually the ratio of the cardinality of the group and the cardinality of the subgroup. So you see, this proof is very simple. You don't have to show anything else. So simple proof is this. So you have to remember this particular process. It's very important, and sometimes the lines which have been written over here, this is actually used. These statements are actually used in different problems. You can get help from this particular theorem. You can take help from and you can use it to different other problems of group theory. Anyways, we have successfully proved our result. This is the Lagrange's theorem, very simple theorem, but very elegant theorem it is. Now I'm going to show you another elegant theorem, and that I'll must say that this proof you always remember, and as long as you require it, otherwise it will not, it is actually meaningless to you. As long as you think that it is important to you, then you have to remember this result and also its proof. And after I show you the proof, then you will get to see that why this proof is so important. You will get to know by yourself. First of all, let us begin with the proof. Let me not tell you what the proof is all about. I'm not giving you the statement. The statement will come. I'm just keeping it as a surprise to you. Okay. So I am just giving you the proof in first, and then gradually when I progress, at the end of this proof, you will get to know what have I actually found. Suppose I'm considering a group. Suppose I'm considering a group capital G whose order is prime. So I'm considering a group capital G whose order is prime, a prime number. And you know, for instance, let us assume the order to be kept small p. Small p is the prime number. And obviously this small p will be greater than 1. Because from the definition of prime number, we know that the prime number starts, when we write the definition of prime number, we say that a number is prime when it is greater than 1 and such thing happen. Other criteria are written. Its only divisors are the number itself and 1. But it has to be the prime number starts, we start counting prime numbers from the number 2. So we have assumed a group whose order is prime number. Okay. Now, since the prime number p is greater than 1, then the group G has an element A which is different from the element E. E is the identity element of the group G. You know, E is the identity element of G. Now, every group contains its identity element. If the group doesn't contain its identity element, then the structure will not be group itself. So this is the primary requirement. Identity element must be present over there. Once in a group you put the identity element, and you know the inverse of the identity element is the element itself. So by keeping the identity element inside the group, you can make it as a group. And thus we always say that the singleton E is a particular type of group, which is a trivial group. Okay. But since we are considering a group which is of prime order, and prime numbers begins starts from it starts from 2. So the group G has some kind of element in it, say A, which is different from E. Okay. We know that and this result we have already discussed in our earlier class, that every subgroup of a cyclic group is cyclic. Cyclic group is cyclic group. We know this particular result. Intentionally, I'm going to do a kind of trick over here. Suppose I'm considering a subgroup. Let H be a subgroup which is of the form as given here. Okay. This is the form of the subgroup. I am considering a subgroup intentionally. This is the trick you have to remember, that that is generated by the number small a, and this small a is taken from the group capital G itself. So I'm considering a subgroup capital H generated by one of the elements of the group in the following manner that we can consider. Now, by Lagrange's theorem that we have proved in our previous page, Okay. The order of this subgroup will divide the order of the group, which is small p. Okay. And since p is prime, then this order of the group will either 1 or the prime number itself, because a prime number is a number which is greater than 1 and is divisible by the number and 1. No other number is divisible, it divides the prime number. So since the order of this subgroup divides order of the group by Lagrange theorem, so this number p, and since the order of the group is a prime number, so order of this subgroup will either be 1 or the prime number itself. But since, according to our choice, this number a is different from the identity, then the order of this subgroup is definitely not equal to 1. And we are left with only one choice, and which is this is equal to p. Now, we know that this subgroup A generated by the member small a of capital G is definitely a subset of the group capital G. And also we have come across the fact that order of this subgroup is actually equal to the order of the group, which is small p. So it is pretty obvious from the above two arguments that this capital G is the subgroup itself, and we are left with no other choice. This is the only condition for which the above criteria will be fulfilled, and this implies that G is a cyclic group. G is a cyclic group. Remember, the statement which I have written here, this is not a part of the proof. This I have only tried to remind you about. Okay, so actually this result, let me erase this result. This result has not been used over here. If I keep this result, then probably you will think that okay, probably I am using this result somewhere, but no. I actually tried to remind you that some sort of result we discussed in our previous class. Actually, the result has not been used over here. So what we have proved in this particular case, we have proved a very important result, that result which I'm going to write right now as a statement of the theorem. So the result is every group of prime order, is cyclic. Every group of prime order is cyclic. So that's why I told you that the result is so important, because if I give you a group and if I mention its order, and if you can identify that the order of the group is a prime number, then you don't have to do any other type of experiments or observations or study on that particular group to know whether it is a cyclic group or not. You don't have, the only requirement is that you can directly conclude from this particular theorem, using this particular theorem, that since the group's order is prime, therefore it is a cyclic group. And you know that in our last class, we also discussed a very important fact, that every cyclic group is a commutative group, if you can remember. We also discussed this result, that every cyclic group is a commutative group. Okay, and therefore this implies that a group of prime order is always commuted. Is always commuted. So remember, these results they are very important to study the groups and their cyclic property. Okay, so probably you have taken the screenshot of this particular proof. Now I'm going to the next section of my today's class, and I think because I didn't get any response from your end, actually I gave you a problem in our through our WhatsApp group, and I asked you to do that particular problem. I don't know whether you have done that problem or not. That was actually not a problem. It was a task which I wanted you to perform because of some reason that I'm going to explain right now. So first of all, I want to ask all the students, did you try with the problem? Because I know that you had other classes and probably didn't get the chance, but still I'm asking, has anybody done that particular checking that I gave you in the WhatsApp group? If not, then after the class later in the evening, you can try that also. Try that. Okay. But whatever I tell you now regarding that particular problem, that you have to believe me. Okay, because you have not done it by yourself, that then you have to believe me. Or if you have done it, then you will get to see that what I'm saying, what I'm going to say is actually telling with what you have obtained by the checking, by the small task that I gave you in the morning. Either you believe me or you ensure your outcome with respect to my discussion. In my last class, we talked about cosets, and I also told you that cosets are very important. What are the objectives of cosets? By defining cosets, we actually try to classify the given group into several mutually disjoint subclasses. That was the objective of the coset. Now, that particular knowledge can be further generalized to some other important topic, and that I'm going to write it as a definition first of all. So my next definition goes like this. What is this definition? Definition says that let capital H be a subgroup. Let capital H be a subgroup of a group capital G if small a belonging to capital G, the subset AH is equal to all such elements of the form A into small h, where H belongs to capital H. We know this, and we know that this is called a left coset. This is called a left coset of H in G that we studied in our previous class. I'm just reminding you the definition of the coset, but the definition which I'm actually going to give you right now is something else. So let me write the definition with a different color. The definition, keep this result in your mind. Okay, this is the definition of left coset, and similarly you can define the right coset also. Now our today's definition is very important. It is saying that let G be a group, let G be a group, a subgroup H of G is said to be a normal subgroup, is said to be a normal subgroup if the left cosets and the right cosets are same with respect to all the elements of the group G. all the elements of the group G. But at the same time, you have to keep in mind another fact, which is also very important. The fact is, however, this is not the part of the definition. It is actually a note, extra note, which I'm giving you. However, even if capital H is a normal subgroup of capital G, this does not always mean that AH is equal to HA for all H belonging to capital H and for all A belonging to capital G, for which I gave you this particular problem, which I wrote in the WhatsApp group. Now I'm going to discuss the problem. Carefully observe the definition and the corresponding note. Whenever I'm saying that this happens, then I can easily say that capital H is the normal subgroup. But if you say that the subgroup capital H is the normal subgroup, that doesn't always mean that the elements of H and elements of G will commute with one another. Very confusing fact. Okay, generally what happens, the definition, whenever we write the definition are always by implication. But here in this particular case, this definition is not a by implication. This is only one way true. For which I actually gave you the problem, and the problem was, you are to consider a group capital G, which is the symmetric group S3. And we know that the symmetric group S3 has these elements in it. We have 1, 2, we have 1, 3, we have 2, 3, we have 1, 2, 3, and we have 1, 3, 2. These are the elements of the symmetric group, if you can recall. Now I'm considering a subgroup capital H. I'm considering a subgroup capital H consisting of only 3 elements: E, 1, 2, 3, 1, 3, 2. Okay, you can very easily show that this is a subgroup of the given symmetric group S3. I'm not going into the details of that. Okay, you do it by yourself. Now, also, if you have done my problem, my task of the morning, in the morning I gave you the task. If you have done so, you will find that if I select all the elements, how many elements are there in S3? There are 6 elements present in S3. So if I consider the elements of S3 one after another, suppose I'm considering E, the identity element, then I can easily show that EH is equal to HE. What does it mean? We shall consider E from here and we select an element from H, say this one. So first of all, we will try to see whether they commute. Then I will fix E and I will select that element and we'll see that that will also commute, and then this one. So E will commute with each and every element of the subgroup capital H. You can also show that if I select the second element, then they will also commute. The second element will also commute with each and every element of the subgroup. So we can easily find that 1, 2, H is equal to H1, 2. We can easily show that 1, 3, H is equal to H1, 3. Not only this, it can also be shown that 2, 3, H is equal to H2, 3. Then 1, 2, 3, H is equal to H1, 2, 3. And lastly, we can also show that 1, 3, 2, H is equal to H1, 2, 3, 1, 3, 2. Now, all the elements for all A belonging to G, for all A belonging to G is equal to S3, AH equal to HA. and this implies that the given H that we have constructed over here is a normal subgroup. Now, showing these things one after another is a huge task. I have just saved the pages of this whiteboard. This task you have to verify by yourself. If you are not agreeing with me, you have to find it by your own, by doing the calculations, and you can verify my statement. Otherwise, you have to believe me that this happens. Okay, so what I am showing over here, that I have considered a group, and I have shown that we can construct a normal subgroup out of that. Anyways, no problem. So we have done so. But interestingly, this can be shown also, that suppose I'm considering the elements. Suppose we consider the element 2, 3 from the group S3. I'm selecting this element, and an element 1, 2, 3 from H. Okay, I'm selecting this element from here. Now let's see what happens. When I select these two elements, and if I multiply them in the following manner, so what we get, let us try to find out. Now you see, first of all, let us start with 1. So 1 goes to 2 and 2 goes to 3. So we get 1 goes to 3. 2 goes to 3 and 3 goes to 2. So we get 2 goes to 2. 3 goes to 1 and 1 goes to 1. So we get 3 goes to 1. And this can be written as only 1, 3. It is a transposition. If you multiply in this manner, let us try to find out what we get. 1 goes to 1 and here 1 goes to 2. So 1 goes to 2. 2 goes to 3 and here 3 goes to 1. So 2 goes to 1. And 3 goes to 2 and 2 goes to 3. So 3 goes to 3. So it is also a transposition. But the above results show us that 2, 3 and 1, 2, 3, where 2, 3 belongs to capital G and this belongs to capital H. This belongs to capital H. They do not commute with one another. Okay, they do not commute with one another. So actually, by the following example, I have tried to show you that the verification of the result which I have written in the note. That we can all the left cosets with respect to the elements of symmetric group, they are similar to the right cosets. H is the normal subgroup, but there is an element of capital G which is not commuting with the element of capital H, although capital H is the normal subgroup. So that result has been verified. Always remember this result, it is very important. Okay, now in the next session, I am going to give you some other important results which are very useful to solve problems. Okay, so I hope you have copied these important proofs and theorems and their proofs. You have taken the screenshot, and if you have not, then you just do so, because I am going to start my next topic in the second session. In this session, I'm not going to write anything further, because if I start, then my discussion will not be complete. So I'm stopping over here. Okay. So these 4 pages are the pages of my first session, session 1. Okay, so let's wait for the next session to begin.